Now, see here the next chapter, that is electromagnetic induction, that is also known as EMI. So, see here in this chapter first we will study about magnetic flux. So, what do you mean by magnetic flux? Already we have discussed about the magnetic flux and also electric flux. As we define electric flux, similarly magnetic flux is defined as. Suppose there is a magnetic field, like this in certain area, that is a B is equal to here. B is a vector, that is a magnetic field. And now I have taken some area here through which these magnetic field lines are passing. So, now if the area is held perpendicular to the magnetic field lines, maximum number of magnetic field lines are passing through this area. So, we can say the magnetic flux is maximum. Suppose area vector of the coil is like this somewhere here, and area vector of the coil is this, that we can take as a vector A here. So, this angle is theta between the area vector of the coil and magnetic field. Now, the magnetic flux through this area is defined as phi B is equal to vector B dot vector A. That we can write here in this case, phi B is equal to B A cos theta. Theta is the angle between the area vector of the coil and magnetic field. And now, see here, if you are taking theta is equal to 0, that means magnetic flux will be maximum, and that flux will be equal to here phi B is equal to B into A, and if theta is 0. If you are taking theta is 90, then we can write magnetic flux is 0 if theta is 90, because cos 90 is 0. And also SI unit of magnetic flux is SI unit of magnetic flux, that means phi B is equal, that is here Weber, and it is represented by WB. And you know it here also, from here B we can write here phi B upon area, that means magnetic flux per unit area is equal to magnetic field. So, its unit is also there, we can write here Weber per meter square. So, Weber per meter square is the unit of magnetic flux density, that is equal to B. So, B is also known as magnetic flux density here. So, this is about the magnetic flux and its unit. Now, see here, magnetic flux can be changed by the three ways. If you are changing B, magnetic flux can be changed. If you are changing area, magnetic flux we can change it, and if you are changing theta also, then the magnetic flux can be changed. So, by changing the three factors like B, A and theta, B that means the strength of the magnetic field, and also A is the area inside the magnetic field, and theta is the orientation, that means if you are rotating the coil, so the theta is changing. So, by changing all these three parameters, we can change magnetic flux. So, now see here, we have seen formula for the magnetic flux, that is phi B is equal to B A cos theta. Now, if you change any one of the factor which are affecting magnetic flux like B, A and theta, magnetic flux will change. So, see here, whenever the magnetic flux changes linked with the coil or through any area, EMF is induced in the coil. As if the circuit is closed, we can say the current is also induced. This current is known as induced current, and EMF is known as induced EMF, and this phenomenon is known as electromagnetic induction. So, simply the phenomenon of the generation of EMF or current by changing magnetic flux is known as electromagnetic induction. So, now let us see certain experiments where we can explain how does magnetic flux change and how does EMF come into the circuit. See here, suppose if you have taken any loop like this in this way, and this loop is here connected to here the galvanometer. I have taken here the galvanometer, and if you take here a bar magnet, these are the Faraday's experiment we are discussing. This is north and south, and this from this north and south magnetic field lines are coming like this. So, as you move this magnet towards the loop, what happened? There is a deflection in the galvanometer is seen here. and as this magnet comes towards the loop, there is a deflection. As the magnet comes to the rest, there is no deflection in the galvanometer. And also, if this magnet is taken away, there is a deflection in the galvanometer, but it is opposite to the previous one. What happened in this case? When you bring the magnet, magnetic field changes. As a result, magnetic flux linked with this loop changes, and because of that, EMF is induced and current flows through this loop, and that current is known as induced current. Now, see here, when you bring here the north pole towards this, so the current will be induced in the loop, which will oppose the relative motion of this bar magnet. It means the direction of current in the loop will be anti-clockwise. So, if the north pole is brought towards this coil, so the direction of the loop current in the loop is anti-clockwise. As a result, this is the upper face of the coil, or the face which is facing towards the north pole of the magnet will act as a north pole, because when the current flows through the loop, it behaves also as a magnet. And now, this north pole will oppose the movement of this magnet here, and to move the magnet, some external work has to be done. That work is converted into energy, and this is actually basically we can say about the law that is called the Lenz's law here. So, here Lenz's law is actually, according to this law, EMF is induced in the coil in such a way that it opposes its cause of production. It means when we bring the north pole of the magnet, flux linked with the coil increases. So, the current will be induced in the coil in such a way which will oppose the increase in the magnetic flux, and this can be done if the polarity of the, or you can say the direction of the current or the is anti-clockwise here, because the magnetic field will be to this side opposing this relative motion, that will reduce the magnetic flux. So, the Lenz's law says here basically the current is induced in the circuit in such a way that it opposes its cause of production, and also the conservation of energy can be justified by using the Lenz's law. Now, see your second experiment, that is the second Faraday's experiment. I have taken here the solenoid where the direction of current is here because the battery is connected. So, one pole is behaving as here the north and another pole is behaving as the south. This side it is behaving as a north and this is behaving as south. Now, there is another coil here that is placed also, another solenoid connected a galvanometer across its two ends. Now, this coil has got magnetic field inside it. So, it is behaving as a bar magnet. Now, we move this coil to this side. As you move this coil to this side, again there is a deflection in the galvanometer. So, when this north pole of the coil comes to this side, so this face of the coil will become as a north, because according to the Lenz's law, and as a result the direction of the current will be here in this one, in this loop, in the first loop is here anti-clockwise. And now, if you take it away, here it will become as a south and the direction of the current gets changed, and the direction in this first loop will be here actually clockwise. So, also here we can get the EMF here, because when we move the coil, magnetic flux linked with this coil also changes. This can be done also in this way. Here, if you do not move, just to vary the value of the current by using the switch here, tapping key. So, first to increase the current or decrease the current, then also you will be getting the EMF is induced in this coil, and that phenomenon is actually known as here the mutual induction. And in that case also here the increase or the decrease of the current in the first coil, in the first solenoid, will be opposed by the induced current in the second solenoid here. So, these are the examples of the electromagnetic induction and the different Faraday's experiment to demonstrate the change in magnetic flux induces EMF. So, there are also Faraday's laws of electromagnetic induction. So, in case of the Faraday's laws of electromagnetic induction, Faraday's laws of EMI, that is electromagnetic induction, we can write here the magnitude of the EMF induced in the circuit is actually given by here we can take EMF by this way. Here the symbol I have taken here the E, and that is equal to here d phi upon dt. So, the magnitude of the induced EMF in the loop due to change in magnetic flux is directly proportional to the rate of change of magnetic flux linked with the loop. And also we can write here E is equal to minus d phi upon dt, and negative sign it comes here, that actually tells us the EMF is induced in such a way which opposes its cause of production, which already we have discussed with the Lenz's law. And also in the loop you will be getting the induced EMF as long as the magnetic flux changes. As there is a change in the magnetic flux stops, it means the magnetic flux becomes constant also, you will not be getting any EMF induced. So, these are about the Faraday's laws of electromagnetic induction. So, here we have seen the experiment and its laws, mathematical laws. Now, we will be doing some question related to this, and also we have done the Lenz's law. See here the application of Lenz's law is very important, where you can use Lenz's law to give the direction of the induced current in the loop.